take that as a no. We're holistically happy. I'll accept blissfully happy. Well, let's try a couple of things and see how we're doing. Let's say, let's take 4x squared plus 3x minus 2 equals 7. Why not? And take a moment and solve for our x. Granted, there's nothing nice about the numbers there. That's going to be a little bit on the ugly side, but that's okay. That's us trying to see where we are. So take a moment, solve that for x. I'll give you a minute or two, or a couple minutes anyway.
I don't know if I'm the only one, but I'm having kind of a hard time hearing you, Matt.
Oh, okay, let me check.
You're not the only one.
It's just kind of muffled. It sounds like.
It sounds like it's one of those mornings.
Yes.
So tell me if this is better or worse.
Is that better or worse?
That is definitely better.
Okay. So if it gets bad again, let me know. But
I will.
thank you. Oh, Dan, you made it. That's good. Welcome. So I'm not wanting to rush us here, but in terms of once you get to practice with these, how long this problem should take, if you imagine, 50 or so minute test and you've got, 10, 11, 12 problems on it, this problem taking more than 4 or 5 minutes would be problematic. So we want to work on making sure, not that we're fast so much. Speed is never going to be one of our goals here. but working through the problem in a smooth and organized way is one of our goals. And a side effect of that is being able to work fairly quickly. So do make sure you're practicing enough to not only get the ideas, but be able to move through the problems in a steady, organized way. But we're working toward that, so that might take a little while, and that's okay. So we have talked about quite a few, well, at least a couple major options for how to approach this problem. We could add over this 2 and complete the square. We'd have to divide the 4 off to complete the square. But we could approach the problem that way. But at the end yesterday, we talked about, well, if we set it equal to 0, subtract off that 7, we could, instead of having to go through the formal completing the square process, which with these numbers would be certainly very doable, but a little arduous, that instead we could mimic that process by using the formula that we developed by completing the square that ideally most of us are familiar with and have some experience with. The good old quadratic formula. Now, it's common to replace this b squared minus 4ac, and well, not necessarily replace it, but separate that off as a discriminant. Ideally, if you've seen the quadratic formula, somebody has presented the discriminant to you, just isolating that b squared minus 4ac. And that discriminant is going to, well, discriminate between, distinguish whether or not this quadratic is going to have 1 answer, 2 answers, or no real answers. So because this is in a square root, all the examples we've looked at so far have had 2 solutions, 2 real solutions. But if this discriminant under here ended up being negative, we wouldn't be able to take the square root of that negative and stay real. So if this discriminant ends up being less than 0, then we still have 2 answers, but those 2 answers will be non-real. And if we're looking for things like x-intercepts or how many puppies it takes to do whatever we're modeling here, if we're whatever we're trying to solve here, if it's has to be a real value, then we could just stop and say, oh, no real numbers, no real answers, we're good. If this discriminant is equal to 0, then we're going to be taking that square root of 0, which is 0, and we'd be adding and subtracting that 0. So we'd have 1 answer from adding the 0, 1 answer from subtracting the 0. So it's kind of still 2 answers, but because we're adding and subtracting 0, those 2 answers would be the same. So we'll have 1 distinct answer. We often refer to it as 1 answer with a multiplicity of 2, because it is 1 answer coming up twice. We'll use that term multiplicity more later on for some other things. But so it's 1 distinct answer, but it is 1 answer coming up twice. If, oh, I said greater than 0 here. Sorry. I think I said less than 0, but I wrote greater than. If this is less than 0, then we have 2 non-real solutions. Sorry about that. If it's greater than 0, strictly greater than 0, so if this is positive, then we can take the square root and get a real number, probably an irrational one, but that's okay. It'll still be a nice real number. And we'll be adding that real number to get 1 solution. We'll be subtracting that real number to get another solution. So we will have kind of the standard expectation of 2 real answers. So it's often nice to find that discriminant first when you're using the quadratic formula. So I'm going to do that here. That discriminant again is the b squared minus 4ac part. So our b squared is 3 squared minus 4 times a, which is 4 here, times c, which is negative 9. So that discriminant is what, 9 minus, it's going to be a plus by the time we multiply those, 36 times 4. I'm doing it in that order for no particular reason. What was that? 9 plus 112 plus 24 is 144. So that's 144. So 153. So multiply that out real quick. And this 153 is greater than 0, so it's positive. So we will get 2 real solutions to this. We'll often want the non-real solutions, so we're going to end up doing it anyway. So we know we're going to get 2 real answers. And the nice part about doing the discriminant is we now know what goes under this radical. So when we want to write out our whole solution, that negative b is just going to be negative 3 plus or minus the square root of b squared minus 4ac. Well, that's the discriminant. So we can just put that 153 there. This discriminant is actually a nice way to kind of separate the operations of this, kind of break this into more steps instead of doing it all at once, which can sometimes be overwhelming. Over 2 times a, the a is our 4. And then simplify that a little bit. Negative 3 plus or minus the square root of 153, which I don't think reduce. Yep, there's a 9 in there. Over 8. So 153 does have a 9 in it. What is 153 divided by 9? 1. Good old long division, right? 63, 17. So that 153 is 9 times 7, so it's going to be negative 3 plus or minus 17, sorry. 3 times the square root of 17, all over 8. If you need some help reducing your radicals, let me know. Yeah, Justin, that's good. Just, practice reducing those radicals. 153 isn't obvious that it's reducible, but there's a nice trick. 5 plus 3 plus 1 is 9. If the sum is divisible by 9, then the number is divisible by 9. Works for 9s and 3s. But I would forgive anybody for not looking at 153 and going, oh, clearly there's a 9. So that's not a big deal, but it is something we want to think about and try to reduce.
If I had looked at it a little longer, I probably would have seen it.
But I'd have forgiven you if you didn't.
Thank you.
Okay. So the quadratic formula does have its own set of kind of meat to it, mechanics we have to go through. I often say if the numbers are bad, the process is going to be a little bit bad no matter what you do. But certainly if you had done this or tried doing this by completing the square formally, then it probably made quite a bit of a mess.
So where did you get the negative 3 from when you did it in that method? Because I did it by completing the square and it was kind of a mess.
The negative 3? Oh, this negative 3?
Yeah, that one.
Well, that's our opposite of b. So this, I don't want that, sorry. This negative b.
I see it.
Yeah, so it's kind of that negative b. And those things, are easy to overlook, particularly negative signs out in the front of things are always kind of irritating. If you did want to do it by completing the square formally, you certainly could. You probably recognized in looking at this that that's a little bit disadvantageous, just because we spent that time with completing the square. We will use it for different things. We'll use it today for different things. We don't want to be tied to it when the numbers are nasty. But if we did want to, I'm going to do this really quickly. Instead, you'd add that 2 over, divide both sides of this by 4, equals 9/4. And then we have to have this and square it. So half of 3/4 is 3/8. 3/8 squared is 9/64. So that 9/64 is going to be added to both sides. Again, I know I'm doing this really quickly. X plus the thing we squared was 3/8 squared equals, we need common denominators here. So that's going to be 9 times 16 over 4 times 16 to get common denominators, plus 9/64. So x plus 3/8 squared equals, what, 143? /64 plus 9/64. That makes me nervous.
It's 153. Wait, no.
No, it's 144.
Yes.
Yeah, okay. And then x plus 3/8 squared equals, that adds up to the 153 that we needed from before. Good, okay. Over 64, square root both sides. X plus 3/8 equals plus or minus the square root of 153. That is an unacceptable 153. Square root of 153 over 8. Nice, our common denominators are there. So when we subtract this from both sides, -3 plus or minus the square root of 153 over 8. And again, that 153 will reduce down. So we get the same answer. It works both ways. And, you know, it took about the same amount of space, I suppose. I was kind of rushing through this. And this one, we did kind of very step by step. So in general, if the numbers are bad, if the numbers are a little bit icky, quadratic formula is often the nicer way to go. Because when the numbers are a little icky, particularly when there's a lead coefficient, and you're having to do all that lead coefficient stuff, it can get a little bit messy. So when the numbers are, or when the quadratic is a little bit on the uglier side, I'll tend to use the quadratic formula instead of completing the square. But if we had a different problem, let's say it was, x squared plus 10x minus, I don't know, 5 equals 7. And we wanted to solve that. We could try setting it equal to 0 and seeing if it factors. Setting it equal to 0 would be what, a -12? What multiplies to 12 and adds to 10? Nothing handy. So it doesn't look like it's going to be factorable. But with a nice lead coefficient of 1, and especially an even coefficient of the x here, completing the square would probably be easier than even going into the quadratic formula. We'd have 10x equals, add the 5 to both sides, 12. And then x squared plus 10x. Half of 10 is 5. 5 squared is 25. And then 12 plus 25. So without all the fraction work in it, because there's no lead coefficient here, and because this is nice and even, completing the square can actually be nicer. So you do want to have both tools for when When one is nicer, use it. When the other is nicer, use that. Now, this might not quite seem so nice because we're, kind of used to quadratic formula from some of our other classes. But once you're used to completing the square, this can be nice and quick in comparison. And you can hopefully see from how I went through this problem that once you get real proficient with it, like once you get real good at completing the square, even that can go fairly fast. But again, if I looked at this problem and had to solve, I'd use quadratic formula. But looking at this one, you could use quadratic formula, it would work, but and you'd have instead x squared plus 10x minus 12 equals 0, and so negative 10 plus or minus the square root of 10 squared minus 4 times 1 times 12 all over 2 times 1, and that's your x equals that. And then you just got to simplify this, so it's not, again, terribly more difficult. It's just often, you're so many chances to make little errors here. So both tools are going to be good for us.
So is it the leading coefficient that differentiates which one's easier to use?
For the most part, yes. That lead coefficient makes a huge difference. That should be a negative 12. Because that lead coefficient brings up all of these fractions, the lead coefficient is a big deal. If this had even been something that wasn't even, if this had been like a 7 and I'm 11, having to have 11 halves and 121 fourths might be enough of a reason not to do this. That's kind of a style issue, I suppose. But it's important to keep in mind that both work in any case because they are the same process. This quadratic formula was built by doing this process with an abstract A, B, and C. So we're doing the same thing either way, really. It's just, are we doing it all by hand, or are we letting the formula handle the sticky parts? If there aren't sticky parts, just do the process. If there are sticky parts, let the formula handle the sticky parts.
Cool.
Now, that all being said, sometimes there are parts that would be super sticky no matter what you did. How about equals 4/3? So now these fractions here, 2/3 x squared plus 1/2 x equals 4/3. Those fractions aren't particularly scary fractions. They're not, 17/93 or something really nasty. But still, you present a problem like this with fractions in it, and even if you're fairly comfortable with all of these processes over here, the fact that this problem is starting in fractions can lead people to panic a little bit. Often when this problem occurs on tests, that should be a hint, by the way. Often when this problem occurs on tests, people who did the first quadratic without trouble will often just leave this one blank because the fractions make them so nervous. So I want you to I'm just going to give you like 60 seconds or so to kind of go, okay, how would I approach this problem using the tools we have? And then I want to kind of talk about some ways to make it easier that you may or may not have employed. I do want to encourage you guys, as I have in the past. You're welcome not to, but you know, having cameras on is nice. It can help us feel more together and kind of allow me to quickly get a read on how you guys are doing and feeling out there. So if you can have, if you're comfortable having your cameras on or willing to have your cameras on, that can be nice and helpful. I do understand it's 9 o'clock in the morning and we don't have to go anywhere, so but I'm sure you're all just adorable, so try not to worry about that too much. Okay, so we could start this problem off by completing the square. Um, I don't want to. That would be icky. Divide everything by 2/3. I don't want to do that. We could go to the quadratic formula, but plugging fractions into the quadratic formula can be messy. It can take something that's a little bit messy and make it even more messy. So with some exceptions, there are definitely exceptions. I do want to say never plug fractions into the quadratic formula if you can avoid it. And frankly, you can always avoid it. But sometimes it's not worth it. But anyway, there's no reason for us to plug the 1/2 and the 2/3 and the 4/3 into the quadratic formula. Well, let me not do that. The reason is we never have to in an equation. We can always get the fractions out of our way. Because in an equation, we always have the opportunity to multiply both sides of our equation by anything we want. So if I was trying to multiply something in here that would get this 3 to go away, if I multiplied both sides of this equation by 3, those 3's would cancel. I'd still be left with the 1/2, but at least that would be better. If we wanted to get rid of the 1/2, we could multiply both sides by 2. Then when the 2 multiplied by the 1/2, the 2's would cancel. So if we could multiply, frankly, both by 2 and by 3 at the same time, we can get both of those things to happen. Well, how do we multiply by both 2 and 3 at the same time? Multiply by 6. When the 6 multiplies by the 2/3, the 3 will cancel with the 3 and the 6, leaving 2. 2 times 2 is 4x squared. Plus, when the 6 multiplies by the 1/2, well, the 2 cancels with the 2 and the 6, leaving the 3, or just half of 6 is 3, however you want to think about it. Over here, the 3 cancels with the 3 and the 6, leaving a 2, and we get 8. Good old-fashioned clearing fractions. It's a tool or a skill that a lot of people get introduced to and then kind of leave on the wayside, but it's a super, super handy skill. We'll use it quite a lot for quite a few things. But boy, didn't it quickly make this question a lot easier. One of the reasons I will continue to stress you guys practicing and getting good with your fractions is because it really does nice things like this if you can work with them to clean things up. I often tell people or joke with people or tease people about if you really, really don't like fractions, and some people don't. Some people really just fractions just drive them nuts. If you really, really don't like fractions, the best thing to do is get really good at fractions, because then you will find ways to avoid having to actually use them. Looking at this and trying to plug all these fractions into the quadratic formula and work out that way, it would have worked, but it would have been a tremendous amount of little fraction work. Being more skilled with fractions allows you to do a kind of more aggressive step here that gets all the fractions out of your way so you don't have to work with them. So if you really don't like working with them, fine, I respect that. get good with them, and you can get them out of your way and not have to work with them. But as soon as we get here, we can, again, we could complete the square here, dividing off that 4 and whatnot. But with those numbers, again, I completing the square would be probably a little bit more irritating. And since we have a nice A, B, and C, going to the quadratic formula would probably be the nicest method. Do that real quick just to make sure we're all happy. So b squared is 9 minus 4 times, it's going to be a plus with that negative. 4 times a times c is 32. So 9 plus 100 and that would be 12, and then also 128. So that's 137. So then our solution is going to be the opposite of that 3. I think we had a 4 and a 3 on the last one, didn't we? Or one of the last ones. So -3 plus or minus the square root of 137 over 2 times 4 is 8. And I don't think 137 reduces now. So boom, boom, boom. That's our answer. So this problem might have looked scary with all those fractions in it, but hopefully cleaning up those fractions and a little bit of practice with your quadratic formula and stuff, this can be a fairly, nice, quick problem if we approach it well. Questions about any of that? Do make sure you practice solving your quadratics. Even when we get out of our section on quadratics, we're going to be solving a lot of quadratics. In chapter 4, we'll be looking how to break down large polynomials. And when we do that, we'll end up with quadratics, and our quadratic skills will take over. In chapter 5 on exponentials and logarithms, we will often, in solving our logarithms or exponentials, we will often have a result that's a quadratic that we then have to solve. So when we get rid of the logarithms or get rid of the exponents, what remains is a quadratic that we need to solve. When we start doing circles and ellipses and hyperbolas in our conic sections, we will have not only x squareds and x's, but y squareds and y's. So we'll have to use these techniques essentially on 2 quadratics at once. So kind of this fundamental skill of being able to solve a quadratic is something you've done in 65 and 95, but it is something we want to be as proficient as possible with, because it's going to come up a lot. And if it stops us and slows us down every time, we're going to get in trouble. So do make sure you're practicing and getting this down nice and solid. Questions about any of that before we move on a bit? Still talking about quadratics, but just some other parts of quadratics. If some questions come up, let me know. So I want to look at a function. I could say y equals, but I want to look at this in a particular form. So x minus 2 squared plus 5. So what we had before, this question and the ones that we did here, these questions were all what we would call a quadratic equation. This is, by the way, a quadratic formula, or the quadratic formula. These are equations that are quadratic, so they are quadratic equations. The difference here is this is a quadratic function. We could either see it this way in function notation or in XY, equation notation. But either way, because we have an input variable of X and an output variable of Y, this is now a function. So first and foremost, if somebody said solve this function, that those instructions wouldn't even make sense. To solve, we're finding a value for a variable that makes an equation true. This function is true for infinitely many X and Y's. The only way we could solve it is if somebody gave us a particular value for the function they wanted. Then we could solve. But this function, there's no solving it. What we can do with it is things like graph it. So ideally, we're familiar with what the graphs of quadratics look like. Anybody real quick want to say what the graph of a quadratic looks like? Aaron, great, parabolas. So this is going to look like some kind of parabola. Exactly where it is, where the y-intercept and where the x-intercepts are is kind of dependent on the particular quadratic, but it's going to look like a, those U-shaped parabolas no matter what. So if we really quickly wanted to, that's going to pain. If we really quickly wanted to determine what that graph looked like and had no other tools, our kind of go-to tool for graphing anything should be, pick some X values, find some Y values, and make a graph. So I'm going to do that just real quick here. Let's say we used 4, 3, 2, 1, 0, and -1. That's just a pile of points for us. And we wanted to plug those in to find Y's so we could plot this thing. Because, we know it's going to look like a U, but where exactly that U is, I need some data. So real quick, plug in the 4. 4 minus 2 is 2. 2 squared is 4. 4 times 3 is 12. 12 plus 5 is 17. Usually I'd let you guys do this, but I want to make sure we've got time here. Plug in the 3. 3 minus 2 is 1. 1 squared is 1 times 3 is 3 plus 5 is 8. By the way, if I get any of these wrong, do yell at me. 2 minus 2 is 0. 0 squared is 0. 0 times 3 is 0. Plus 5 is 5. 1 minus 2 is -1. -1 squared is +1. Times 3 is 3. Plus 5 is 8. 0 minus 2 is -2. -2 squared is 4. Times 3 is 12. Plus 5 is 17. You notice the symmetry going on. -1 minus 2 is -3. -3 squared is 9. 9 times 3 is 27. 27 plus 5 is, 32? So we can come up with some points fairly quickly. If you had a calculator, you could have it give you a table. Frankly, the calculator could graph it for us. So we've got some options there. But if we wanted to plot this, we could plot some of these points. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I like putting that longer one at 5. It helps people see what's going on. I'm not going to put a Y scale on this right now. But if we went to 4, at 4, we'd be up at 17. So we're calling that 17. At 3, we'd be at 8. So 8 by comparison would probably be about there. At 2, we're at 5. At 1, we're back to 8. At 0, we're back up to 17. At -1, we're way up at 32, wherever that is up here. And hey, we've got a nice, slightly squiggly, but a nice parabola. So anytime we want to know what our parabola looks like, we could do that. We could plot a whole bunch of points and try to make a drawing, but that's going to be time consuming. I want you to notice that bottom point there, the point that made this vertex. The reason that this bottom point, this 2, 5, is so special, the reason why it's that lowest point, is because this 2, when we put it into our formula, that 2 made this 0. And because this is squared and can never be negative, the smallest value this will ever output is the number that makes it a 0. Notice when it was negative and we squared it, they became positive, so they were bigger. If it was positive, squaring it stayed positive, and it was a larger number. That 2 made this little piece inside the perfect square 0, and thus made this whole thing the lowest it possibly could be. So if somebody gave us a different quadratic function, say y equals x plus 5 squared minus 13, and we want to know where is this lowest point, where is that vertex? Well, that vertex is going to occur in the same way. It's going to occur in what makes this term 0. So what x value is going to make this become 0? Let you guys throw that up in the... Okay. Aaron? Yeah, -5. So if our x is -5, this is going to become a 0, and it's going to be the lowest possible value. And the nice part, if this is 0, then our output is the only thing left. It's going to be this constant out here. So -13. Just like this 5 was the y value for that vertex. So whatever this quadratic might look like, we know that it opens upward because the lead number out here is a positive. It's +1, but it's a positive. And we know the vertex is going to be at -5, -13. And it's going to open up from there. Cool. So this is a really handy tool, even if we have something that looks a little bit uglier, 5 times, even if it's a -5, say -5 times x minus 7 squared plus 12, 7. If somebody came up to us and said, hey, what's the vertex? As long as we're in this form, the vertex is ready for us. People often call this form of a quadratic the vertex form of a quadratic, because the vertex is sitting right here. What makes this become 0? Well, the 7 would make it 0. Do notice we take the opposite of the sign that's there because we're trying to make that a 0. And when that's a 0, 0 squared is 0 times anything is 0 plus 12. So 12, that's our vertex. So if we graphed it, over 7 up 12. So that 0.712. Now, because of that negative multiplier out in front, it's going to open down instead, but we still know where that maximal point is. So having quadratics in this form, in this vertex form, it's usually y equals a times x minus h squared plus k, picking out our vertex, hk, is really handy. Somebody hands you something like this. Hey, here's my vertex, 712, that was my vertex. Why might we care about vertexes, or vertices, sorry, as the plural? Well, vertices are our minimums and maximums on quadratics. Anytime we're trying to find a minimum value or a maximum value, minimizing costs, maximizing revenue, we want to find a vertex. So, having an equation in this form makes finding a vertex really nice. But you can probably imagine people don't always hand us our formulas in this form. Oh no. What if somebody did give us, say, y equals, oh, I don't know, how about 2, do I want a 2 there? Sure. 2x squared minus 6x plus 1, and told us to find the vertex of this. Well, finding a vertex in this form was super handy. So wouldn't it be nice if this was in this form instead? Gosh, if only we had some sort of tool or method for making a little perfect square like this. Now, we used quadratic formula instead of completing the square over here, but we're not solving a quadratic set equal to 0. We're trying to change the form of a quadratic function. So the quadratic formula is actually not helpful here. We actually need to build this little perfect square right now for this. But the nice thing is we can complete the square. We know how to do that. We'd have to factor out that 2, divide out that 2, x squared minus, it is handy that this is divisible by 2, so 3x. And actually, I'm not even going to divide that 2 or factor that 2 out of the 1. I don't need it factored out of the 1. I'm going to leave it separate. This might seem a little weird, like are we allowed to just factor out of those 2? Well, as long as if we redistribute, we'd get back to this, which we would. That's perfectly reasonable, perfectly allowed for us to do. What do we have to add? Notice I'm not dividing the 2 off on both sides. I want this y to stay as a clean y equals. So I'm going to do all the work on one side here. So x squared minus 3x. What do we have to add to make this perfect? I'm imagining hearing all of you in my head saying, well, divide the negative 3 by 2 and square it. I don't know why you guys talk in that voice, but so we get 9/4. So we got to add 9/4. Now, usually I'd want to add 9/4 to both sides, but because I want this to stay as y equals, I want to be able to work all on one side. So I'm going to end that parenthesis because this is the thing we want to factor. But there is another way to compensate for adding 9/4. Instead of adding 9/4 to both sides, if we add 9/4 to this side and subtract 9/4, well, adding 9/4 and subtracting 9/4 would usually end up giving us a 0. So we've kind of added nothing to this side. if that parenthesis wasn't there, this would be plus 9/4 minus 9/4. And we could end the parenthesis there if we wanted, plus 1. And instead of adding it to both sides, we added it and subtracted it to one side, but this is a 0. I can, there's a 0 anywhere you want. The trouble is, if we want to isolate just this part, we have to make sure that when we subtract that 9/4, we notice that we didn't just add 9/4 here, we added 9/4 times 2. That 2 essentially has to distribute, and we have to subtract 9/4 times 2. Sorry, that 2 didn't look, clean that up. So that is the nasty part to be careful about not forgetting when you're completing the square all on one side like this. If we added 9/4 inside here, we really added the product of 9/4 times 2. So we have to subtract the product of 9/4 times 2. That can take a little bit of getting used to. But to finish this off, because I do have to let you guys go, this, and we'll practice this more tomorrow to be sure, but this now factors, and we know it factors into x minus 3/2, because that negative 3/2 is what we use to complete the square. And then we just have to add this stuff together. Cancel those 2's. We'll have 9/2 plus 1, but make the 1 2/2, so we have common denominators. And y equals 2 times x minus 3/2 squared, minus 7/2. So when we're now asked what the vertex is, in this form, we can't see the vertex at all. In this form, the vertex is sitting right here and here. The vertex is going to happen at 3/2. Again, make sure you change the sign, because we're asking what makes this a 0. 3/2 would make that a 0 and leave us with the negative 7/2. So this is another example of using completing the square to perform a useful operation. This one is finding a vertex. This was allowing us, and this was allowing us to solve a quadratic. This was allowing us to find the vertex of a quadratic. We came up with the quadratic formula, so we can technically avoid having to complete the square over here. But for right now, this is what we would need to do to find a vertex. And again, we'll have other uses for completing the square. So we'll practice this more tomorrow. Any questions you guys have before you wander off? I do want to remind you, I put scores on your discussion board stuff. I do want to remind you, each week you need 1 post and 1 reply. So a lot of folks had 1 post but didn't have any replies. So you'll notice your scores on those aren't great. Because it's our first one, though, our first created one, I am going to modify those so it doesn't hurt anyone for this week. But in the future, as we go along, make sure you're doing both 1 post and 1 reply. And again, feel free to do more than that as you guys talk about more, as there's more to discuss as we fight with more things. But do make sure that you recognize that you need both of those pieces. Cool?
What do you mean by 1 reply? Like a reply from someone else, or like you reply to someone else's?
You reply to someone else. Yeah.
Okay.
It's like, my post wasn't compelling enough. I didn't get any replies. Yeah, no, that's fine. Just make sure you're replying to somebody else. And ideally, you guys are, as I said, as we use this more and more, ideally you guys will get into discussions about things and you won't be having to kind of force that. But for a while, to build the habits of using those tools to communicate, it might take a little bit of forcing yourself. But ideally, after a while, it'll just be almost just second nature. Okay, if you come up with any questions before tomorrow, send me a message, send me an email, let me know. And as always, have a wonderful day.